Hello and welcome back to part 3 of this video series about electromagnetic interference in relation to multicopters. Although there is still much to talk about, this will be the last video of this video series. As said before in my previous videos, my main goal is to answer the question: is electromagnetic interference caused by electromagnetic induction made up? Or is it something real that can cause serious problems? If this is the first part of this video series that you are watching, I strongly recommend to watch the other videos first. This makes it easier to understand the terminology. I'll put links to these videos in the description. Please note that during all the previous experiments I only used a small motor and a relatively strong battery. It's important to understand that multiple motors, different ESCs and different flight batteries can generate larger and faster changing current spikes and thus more EMF/noise. As I discussed in an earlier example, the only way to adequately filter this type of noise is by using a voltage regulator with a good PSRR. This, however, is not possible for digital signals. Analog signals used in receivers, transmitters and GPS modules, for example, are way more sensitive when it comes to superimposed noise caused by the EMF. The advantage is that the frequency of the transmitters and receivers are significantly higher than the frequency of the superimposed noise. But still, an EMF that is superimposed on an analog signal can cause electromagnetic interference. Take this GPS module for example. The antenna is on top and there is a complex filter network on the bottom to prevent interference that can be caused by signals that are picked up by the antenna. But still, in all these traces on the bottom side of the GPS module, electromagnetic induction can create noise that can have a negative effect on the reliability of the GPS module. And that is one of the many reasons to have the GPS module as far away as possible from high current wires. But still, problems can occur when an induced EMF manipulates the analog signal. Now, it's not possible to define the point when problems will occur. The important thing to remember is that electromagnetic interference is not made up and can cause very realistic and head-scratching problems. Some problems that can be caused by electromagnetic interference are unstable flight behavior, short transmitter-receiver range, bad GPS reception during flight, main program lockup or the flight controller just stops functioning, twitching ESCs, corrupted serial data transmission, random receiver signal inputs, etc. And these problems can be completely random. During the rest of this video, I will show some examples about how to reduce electromagnetic induction. One way, of course, is to keep the wires away from the battery wires where the electromagnetic field is weaker. In some cases, this isn't always possible due to the lack of space. Another option, when referring to the Faraday-Lenz law, is to reduce the surface area of the closed-loop circuit. For those who have seen the YMFC 3D video series, I did this with the wires that are connected to the gyro. When reducing the surface area by twisting the wires, the EMF decreases, causing less noise in the wires, as you can see in this example. And this method will also work for the clock pulse. Remember the example from the previous video? This is how it looks with the twisted wires. The last thing that I want to cover in this video is shielding. In this example I have an oscilloscope set up as I did in my previous videos. The exact amount of EMF is not important at this point. I just want to show you what happens when I slide a piece of copper clad board between the battery wires and the probe of the oscilloscope. As you can see, the amount of noise is reduced significantly. This is because the changing magnetic fields induce eddy currents in the copper clad board. The magnetic fields created by the eddy currents oppose the electromagnetic fields of the battery wires. This reduces the amount of electromagnetic fields reaching the probe of the oscilloscope. A good example is the floating coil demonstration, as you can see here. The two magnetic fields repel each other and the coil starts to float. The resistance of copper is very low, as you can see here. The resistance of aluminium foil is a little bit higher, but will work fine for shielding. Here I slide a single piece of aluminium foil between the battery wires and the probe. As you can see, the amount of noise is reduced. And this example shows 2 layers of aluminium foil. 2 layers reduce the amount of noise even further. Now, although carbon fiber is conductive, the resistance is not low enough to create strong eddy currents that reduce the electromagnetic fields reaching the probe of the oscilloscope. As you can see here, the resistance of a carbon fiber board is relatively high in comparison to aluminium or copper. So in short, what can we do to prevent electromagnetic interference caused by electromagnetic induction? The most important one, of course, keep the low voltage supply signal wires separated as far as possible from high power wires. Keep the low voltage supply and signal wires as short as possible to reduce the surface area of a closed loop circuit in a changing magnetic field. Twist the low voltage supply and signal wires to reduce the surface area of a closed loop circuit in a changing magnetic field. Keep motor and battery wires as short as possible to reduce the surface area of the magnetic fields. If you use a step down or step up module, place it as close as possible to the component that it is supposed to power. And for shielding, you can use a solid conductive flat surface like a copper clad board, copper foil, an aluminium plate or aluminium foil. Now I hope that you learned something useful about electromagnetic interference. If you think that this video might be helpful to others, please share this video series on your forum or social media so everybody can benefit from it. Thank you for watching and see you next time.